Electron configurations of the full periodic table. Determining the electron configurations for all the periods of the table beyond period 3 is a little more complicated due to the addition of groups 3 through 12. The first 3 periods of the main group only have s and p orbitals. The additional groups add d and f orbitals. But the method for determining electron configuration remains the same, and our use of shorthand notation will make it easier. This chart shows how electrons fill orbitals. Let's start with a closer look at period 4 first. It's right over here. To find the configuration of titanium, which is right over here in green, start at argon, the noble gas, in the period above it, and add electrons as you move to titanium. Place them in the correct shell by using the bottom chart to note the orbital for each electron. So we start with the noble gas in the period above, and that's argon in brackets. Then we come down over here, and we go until we hit titanium. So we have 4s2, that's that, and then we count over 2 electrons in the 3d shell. So that's going to be 3d. All right, that looks a little tricky, right? We went from 4s2 down to 3d. The electron configuration of titanium is argon, then 4s2 and 3d2. And we pointed out on the previous slide how that looked a little unusual. We went 4 and then down to 3. Titanium only has 2 valence electrons. The 2 electrons in the s orbital, 4s2, that is the farthest orbital from the nucleus. The 2 electrons in the d orbital, 3d2, are nearer the nucleus since their n is equal to 3. That's their energy level. Here's the key point right here. Electrons in d or f orbitals are never valence electrons. Throughout the main group, the number of valence electrons equals the units digits of the group number, which I think we indicated a few slides back. In this case, there are 2 valence electrons, and this is group 12. The rule has exceptions for the transition metals, but that's going to be held off until we get to AP chemistry. Let's try another example. Find the electron configuration of germanium. Right over there. We start with the noble gas in the period above germanium, and that would be argon right over here. So we put that in brackets, Ar. Then we go down to the period that germanium is in. We pick up 2 4s electrons right over here. Then we keep going and we pick up all the d block electrons, and there's 10 of them. So that's 3d10. And finally 2 more electrons in the 4p level, and see how that matches with germanium? So then we get 4p2. So we have argon, 4s2, 3d10, 4p2. There are 4 valence electrons, the 4s2 and 4p2 electrons. Next, find the electron configuration of arsenic, right over here. So first we find the noble gas in the period above arsenic. So arsenic is here, the period above, here's argon. So we put argon in brackets. Then we go to arsenic's level, right, the 4th period here. So we pick up 2 s electrons here, so that'll be 4s2 because it's in period 4. We pick up all the 3d electrons, so that's 3d10, and then we count over 1, 2, 3, 1, 2, 3, and we get 4p3. So what do we have for arsenic? I'll just erase those. We have argon, 4s2, 3d10, and 4p3. Finding electron configurations in period 5, right, that's over here and also here. Here's our electrons. It's the same procedure as in period 4, but instead of starting with argon, okay, we're going to start with krypton, because krypton is in the period right above your period 5 elements. So find the configuration for tin, and tin, the symbol is Sn. So we start with krypton, which is the noble gas in the period above tin, and we put it in brackets, so krypton with brackets, and then we go down to period 5. We pick up the two 5s electrons, we pick up all 10 4d electrons, and then we count over to 10, and we just go 2 more. So that would be 5p2. So the valence electrons are in the fifth shell, the n equal 5, right? 4d10, those are not valence electrons. So there are 4 of them, 2 in 5s and 2 in 5p. Periods 6 and 7 in the periodic table are different, as the F block, right, because we're going to start filling those shells, is hidden within the D block. That's done to make the periodic table more compact, but it is very important to recognize that there are 14 elements in period 6, between atomic number 56 and 72. They are normally not shown within the periodic table. They are shown below it. There are also 14 elements in period 7, between atomic number 88 and 104, that are normally not shown within the periodic table. That's illustrated in the next 2 slides. First, this is what you see most of the time when you see a periodic table. And then second, what if we placed all the elements within it in the right place? Here's a fairly standard periodic table. And you have this blank over here. Those are elements 57 through 71. And they squeeze, all of them squeeze into that little block. Then below it, you have the actinide series from atomic number 89 to 103. And all of them squeeze into this little block. So on the next slide, I'll give you some more information on what that actually means. So here's the problem and why all of these elements here are typically shown at the bottom of the periodic table. Because if we put them in the right place, this table gets too wide. It gets so wide that everything has to be compressed. It becomes hard to read. But when figuring out electron configurations, these hidden elements represent f orbitals that need to be filled. That's taken into account on the next slide. So let's find the electron configuration of lead, and the abbreviation for that is Pb. So we have our extended chart here, where we have the lanthanide and actinide series put where they belong, and they're named after the first elements in their section there, okay, La and Ac. So hopefully you can see here's your F block, which we're going to fill. And then, of course, we have the D block again here, and then finally the P block. We go to the noble gas in the period above lead, and that's going to be xenon. And then we start on period 6 and go all the way until we get to lead. So down on the electron model, we have 2 6s electrons. Oh, and by the way, notice xenon here is in brackets. Then we go through the entire F block. And we pick up 14 electrons there. And then finally we go through the whole D block and we pick up 10. Now notice the F block is 4F, the D block is 5D. And then finally we wind up with 2 electrons in the 6p block. So there's a lot of electrons here that don't count as valence electrons. We only count the electrons in the n equals 6 shell, so we have 4 valence electrons for lead. When using a standard periodic table, you just have to remember the 4f and 5f orbitals that are hidden in periods 6 and 7. So here's your standard periodic table here, but within 6 you have the 4f, and within 7 you have the 5f. So you can click here to view an interactive periodic table that shows the orbitals for each element.